Okay, welcome back for part 2 of lecture 13 on hyperparameter optimization and automated machine learning. In the first part, we learned about hyperparameter optimization, and I gave an introduction to the general scheduling and selection algorithms there are, and also when to use which kind of algorithm. For the second part, I want to show a bit of how hyperparameter optimization is actually used in scientific machine learning applications, and also introduce two libraries, Raytune, which is especially suited for distributed workloads in the cloud or on HPC, and AutoGluon, which is a library suitable for automated machine learning on tabular data. Okay, we will start with a bit of my experience on doing hyperparameter optimization on different data sets. So for this example, we're going to look at two computer vision data sets. One is Cypher10, probably one of the most well-known computer vision benchmarking data set. The other one is ImageNet, which is similar, a very well-known benchmarking data set. And you see that they are very different in size. So Cypher10 is really small. ImageNet is a bit larger with 300 gigabyte. But then when you're really moving to big scientific problems, such as, for example, computational fluid dynamics, we have this actuated turbulent boundary layer data set, which is 8.3 terabyte of data. So this is really quite large. And you see that, in this case, you really need things like the cloud or HPC to compute your trials, just because the data is so big. This is not something you can do hyperparameter optimization on your local machine. Now, the basic types of neural networks that I applied to these data sets are, on the one hand, these classical residual neural networks, which I think you've also touched upon briefly in earlier lectures. So in these cases, not only each layer is connected to the following layer, but you have these so-called skip connections, which take the input and add it on top of later layers. And the hope is that these skip connections then can help improve the information and especially the gradient flow throughout the network. On the other hand, so these kind of residual networks are very much used in computer vision, and especially on these two data sets, we're using them for image classification. So you want these networks to learn what whether there's a dog or a cat in the image. Another approach are autoencoders. What these models do is that they take an input, then apply compression to this input. So this means that you end up with, you start out with a big layer, big convolution layer, for example, and then you get smaller and smaller layers. So you end up with a small so-called latent space. And from this latent space, you again increase the size of your neural network layers to reproduce the original input you had in the beginning. And why we do this is that we then have this latent space here in the middle, where there are some very compressed information about our problem available. And this autoencoder we apply to this very large data set from the computational fluid dynamics domain. So I'm going to show you some performance analysis of some hyperparameter optimization methods. And what I did in this case was to, for both of these models, optimize the number of convolutional filters and number of convolutional channels, optimizing the learning rate and warm-up of the learning rate, as well as the weight decay parameter. So yeah, in this table presents a evaluation of the different scheduling methods I've shown you earlier. What's interesting to see here is what happens when you compare random search, which is like, as I mentioned, the smaller, the simplest thing you can do when you do hyperparameter optimization, and when you compare that to more sophisticated methods. So, for example, on the on the two computer vision data sets, we see that the performance of random search is roughly maybe 2 to 3 percentage point worse than the sophisticated method. So you get a classification accuracy of something like above 70% with Bob, but just by doing random search, you already get 68%. So we see in these cases, there's not that big of a difference from using a simple hyperparameter optimization method compared to using a sophisticated method. And the reason for this is that in general, convolutional neural networks are, of course, already heavily biased towards computer vision data sets. So we don't see really large improvements here. However, the very interesting thing is that when you look at the CFD use case here, so this was actually done with a smaller data set, with a smaller section of the big data set, to also reduce the computational workload here. But we see quite interestingly that, for example, Bayesian optimization here has almost 50% improvement compared to the random search baseline, which is a very good thing. And we see that apparently these autoencoder models that I've shown here, it just has not been in the community, not been so much optimized already for this problem as the computer vision problem. So in this field of science, for example, you get a really large advantage from doing hyperparameter optimization. What's also interesting to observe is here that sometimes this population-based training can fall into local optima. So you see that they always get worse performance here than the random search baseline, which is, of course, not what you want. So in this case, you would need to apply probably some regularization techniques to avoid this. Another example from colleagues at CERN is that they use hyperparameter optimization to improve their particle reconstruction method. The base neural network here is a graph neural network, which they use for reconstructing their particles. And the interesting thing that we can observe here is that on the left side, you see the training and loss curves before doing hyperparameter optimization. And once you have applied hyperparameter optimization to this network, you see a quite substantial improvement of roughly 40% to the validation loss. So this is, of course, a great example where hyperparameter optimization can really help in the sciences. Another example is hyperparameter optimization for CT super resolution. So there's this CT data in the medical field available, but maybe the resolution of this data is not high enough to really get insights from it. So what you do in this case is that you apply a super resolution network, which increases the resolution of your input images to help gain or to help gain more insights from them. The super resolution network is again a neural network with hyperparameters that you can optimize. And what colleagues have been doing here is to take the Azure algorithm and apply it to the super resolution network. And here again, you also see that just taking the one of the points here at the top compared to the optimal model here at the end, that this results in a difference of maybe 1 to 2 orders of magnitude in terms of mean squared error. So you see, you can really get a much lower loss here by doing sophisticated hyperparameter optimization. One more medical application that we've worked on together with a colleague is to improve the pneumonia detection score of a convolutional neural network by up to 23 percentage points. This was again achieved using sophisticated algorithms such as ASHA or Hyperband, or also population-based scheduling. So again, a very nice example of how powerful this method is. And another colleague of mine performed hyperparameter optimization for a sound localization model, also a neural network. And here we see that by taking this HPO process from a local machine to a supercomputer, and really using the parallelism there, you get a speed up of the runtime from 3 days to 3 hours, which really shows you that it's really worth it to move your HPO workloads to the cloud or to an HPC system and take advantage of the parallelism that is available there. So to show you a library that is really good at doing distributed hyperparameter optimization in a parallel setting, we're now going to look at RayTune. RayTune is a Python library which is open source but maintained by a company, Anyscale, and it provides you with very simple primitives to build general distributed applications. And the goal that they have is to parallelize your code from running on a single machine to running on a large cluster with very few code changes. And it also works with lots of different, it's compatible with lots of different libraries, but we'll take a look at that later. Within Ray itself, there are also different libraries available. So the most interesting for us is, of course, RayTune, but Ray also has its own training library. It was called Ray SGD. Now I think it's called Ray Train to train your neural networks. And for reinforcement learning, it also has the RLlib available. Ray can be configured with very little work on all big cloud providers, AWS, Google Cloud, Microsoft Azure, for example, but it also runs on a HPC system via Slurm, and also actually runs on your local machine probably. The focus on RayTune, as already mentioned, is on distributed hyperparameter tuning, and it is compatible with multiple machine learning frameworks. So the most common one are probably PyTorch and TensorFlow, but you can also use sklearn, MXNet, or Hoverwood with it. It has logging capabilities for lots of other different libraries. For example, you can do the logging with weights and biases or MLflow. And the nice thing is that it's also compatible with lots of optimization and scheduling algorithms. So basically all algorithms that I introduced to you in the first part of the lecture are already implemented in RayTune and are ready for you to use. So when looking at the workflow, it has 3 steps. You would first set up your problem, then define your search algorithm or your scheduling algorithm, and then call tune.run to run your HPO workload. And afterwards, there are also some analysis capabilities. As I said, RayTune is suitable for distributed HPO. So let's take a look at how it does that. So the way this happens is that you will first launch the head node. And then you would manually also launch the worker nodes and connect them to your head node. Once this connection is active, the head node then will start launching the trials on the worker nodes. So if you have, for example, 1 GPU per worker node, the head node would assign 1 GPU, 1 neural network to each GPU with a different parameterization. Then the worker nodes would start the training of that neural network. And when we do early stopping after 10 epochs or so, these worker nodes will report back the metric, like the current training or validation accuracy, to the head node. And based on this information, the head node then performs optimization and basically decides which trials to continue and which trials to stop. The nice thing here is that once you have set up that connection between the head nodes and the worker nodes, basically RayTune takes care of all the scheduling, all the communication. So it really, it's really efficient to use this library. In terms of integration, RayTune is very simple as well. So you would first need to call ray initialize the library with ray.init. Then you would set up your search space as a dictionary. So which kind of hyperparameters you have and which intervals you want to sample them from. Then you define your scheduler and your reduction factor. You would define how many CPU and how many GPU resources you want to use per trial, and define how many samples you want to evaluate in total. Of course, you need to pass the Python function that performs the actual training. And then you would just call tune.run to perform the training. And in the end, when your training is done, you can shut the whole Ray cluster down again with Ray shutdown. Once your training is done and you have all your results available, as I already mentioned, you can log those to weights and biases. And then you can create these nice parallel coordinate plots. So basically each line in this plot is a trial, and we can get quite a few information just from looking at this. For example, what's very interesting to observe here is that we had a choice to take either 2 or 3 layers, and we see that apparently choosing 2 layers yields the highest accuracy here. So in this case, it's not always true that larger models yield better accuracy. But we see again that a high number of convolutional filters seems to be important here, because almost all high-performing models have this high number of convolutional filters, and all models that have lower number of convolutional filters get a much worse performance, actually. Another nice thing about Ray is that it offers 2 levels of parallelism. So you can not only run on the RayTune level multiple trials in parallel, but you can also distribute the neural network training or the machine learning training itself, and have, for example, multiple GPUs work on the distributed deep learning. This is orchestrated either by Horovod or PyTorch DDP, for example. Just a quick refresher on distributed deep learning. So this is especially becomes important when you have very large data set, such as I have shown you in the beginning. And what you can do with these large data set is that you split up your data set, and each GPU takes a different portion, trains its local, so each GPU gets a part of the data set and the same model. Then they train the model locally on that data set. And once all GPUs have finished that, they would synchronize the gradients between GPUs and apply a single or do a single optimizer step here. So essentially what's happening here is that you have multiple trials training in parallel, but then each of these trials via this data parallel training approach would also work on multiple GPUs to speed up the training process. And one thing that comes up here that you need to be aware of is that, of course, in this case, there's a resource allocation trade-off. And what you need to decide here is whether you, on the one hand, either want to enforce trial parallelism, which means that you are putting more, so assuming you have a fixed amount of GPUs, you're putting more GPUs to the data parallel training loop of all of your trials, which means that the trials will run faster, of course, but you do not have so many trials training in parallel. Or if you want to enforce more HPO or NAS parallelism, so this means you're using fewer GPUs for each trial, but on the other side, have more trials running in parallel. And this is something where, you can do some interesting trade-off studies. We did that, for three algorithms: Asha, Hyperband, and random search on a benchmarking data set. And what we see here is that the more GPUs we have per trial, so the green line here, usually also leads to a faster improvement of your HPO workload in the beginning. So we see that really the green line in all cases has the steepest increase in the beginning in all cases. However, we also see that this means that the trials run for the longest, so that we see the runtime for the green line is always the longest, while the runtime for when we have fewer GPUs per trial, which means that we have more trials in parallel, the runtime in all cases is very short. So the orange or blue line always has a shorter runtime compared to the green line here. And this is something to keep in mind, whether you want really that fast improvement in the beginning or whether you want a faster overall runtime. Okay, this is Raytune, a library that's very suitable for basically any type of machine learning model. And due to this two levels of parallelism here, it's actually very suitable to apply this to large models, large data sets from basically any scientific domain. However, if you are more working with tabular data, which is also an option, in this case, it might be worth it to look at AutoGluon. So what is AutoGluon? AutoGluon is a library which was developed by Amazon Research to perform automated machine learning. As I already mentioned, it has a special focus on tabular data and especially on time series prediction. When you think about it, there are actually tons of problems that you can apply this to. And usually I would say tabular data and also time series data is not so large in size. So it's very seldom that you have really gigabytes of tabular or time series data. So the size of the data set is usually much smaller. So in this cases, it probably would be interesting to take a look at this AutoGluon library. You don't need the parallel computing power spanning hundreds of GPU with RayTune in this case. What AutoGluon does is that it under the hood combines different state-of-the-art models, and for the combination of those, it uses a weighted ensemble at the end. These state-of-the-art methods include classical regression method, but also neural networks. And they also have access to this Kronos foundation model, which is a very large foundation model trained on large amounts of public time series data as well as synthetically generated time series data. It is based on the transformer architecture and has just very good general forecasting capabilities. Also already on its own. But the main advantage here is that AutoGluon combines all of these things together in this weighted ensemble. So what you're getting in the end is a very good performing model. But of course, also one has to say, because you're combining so many models and have this weighted ensemble, you're losing a bit the interpretability that you would maybe have if you're using just one simple regression method. But on the other side, of course, with neural networks, you usually, in all cases, only have a limited interpretability. Let's take a brief look at this Kronos foundation model. So it's based on the transformer architecture, which is mainly used in the field of natural language processing. And what they do here is to first tokenize the time series to get these single tokens. And then for the training, use an autoregressive transformer with similar way as you would train a language model. They are doing, based on these tokens, next token prediction. So given a selection of tokens, the model is asked to predict which token is most likely to come next. And then during inference time, they again, of course, convert those tokenized time series back to actual time series to get a real prediction. The nice thing about AutoGluon is that it includes a probabilistic forecast. So it not only predicts the mean of your forecast, but also gives you the quantiles. And this really helps you to assess the accuracy of your prediction and can be very helpful, also in the cases when you do time series forecasting, where you maybe want to know how sure the model is about the answer that it gives you. Okay, so to sum things up, this is my last slide. I would like to encourage you, when you build machine learning models, to use systematic HPO methods instead of just doing trial and error by hand. As we've seen, depending on the domain, this can really result in much better models than you as a human would probably design. I would encourage you to use parallel computing resources for the HPO process, especially to run multiple trials in parallel. We've seen that with Ray, for example, there's a good library available that can help you do this. And if you have access to a cloud or an HPC system, it's really something that's worth to try. These are my references, and with that, I thank you for your attention. Thanks a lot, Morris, for giving me the opportunity to hold this lecture, and then hope to see you in Iceland. Bye-bye.